Good afternoon and welcome all. My name is Mark Richardson with Vibrant Technology. I'm the marketing manager, and I welcome you to another Mescope webinar. Today we are doing a Mescope Modal. We're specializing in rapid impact testing with a two-channel analyzer is the title for today's seminar. Before we get going, I did want to have a few announcements here. We are going to be exhibiting at IMAC this year down in Austin, Texas. IMAC is the International Modal Analysis Conference, and the dates for that are February 13th through the 16th. We will be exhibiting, so if you are going to be attending IMAC this year, please stop by and visit us at the booth. In addition, we will be doing a presentation, I believe it's on February 14th. Is that correct, Brian? Tuesday?
Yeah.
Yes, okay. I believe it's sometime in the afternoon after lunch. We are doing a presentation on video analysis, video ODS. So please stop by and visit us there if you're attending IMAC this year. One other announcement I wanted to mention, we have our partner, Jim Steedman at NavCon Engineering is having a training class on February 20th through 23rd. That is a hands-on 4-day modal testing and analysis seminar located in Fullerton, California. And you can see on your screen there, we got a few pictures of what's taken place there. Lots of good stuff, though. This is the premier modal analysis training. If you are a current Mescope user or you are new to Mescope and want to learn some hands-on modal and ODS training, this is where you need to be. In addition, Jim's got some additional classes coming up. If you can't make it to February, there is one in May. And then I believe, let's see, we got May 22nd through 25th, and then on into the summer, August 14th and 17th, and then into the fall, November 13th and 16th. You can get all the information on those training classes at navcon.com, navcon.com. And let's see here, moving on, just a reminder, this webinar is being recorded. We will get a recording up on the YouTube site here in a couple days. And you can find that just by going out to YouTube and then typing in Vibrant Technology. We've got all of our past webinars. We put a recording up there on YouTube, so it's real easy to find. Lots of good tools and training information out there on the YouTube site. And we are going to be following, this webinar is following App Note 54, which is called Simulating a Rapid Impact Test. If you, on our website, vibetech.com, you can click on the resources tab, and if you have a current Mescope license, you can actually download the App Note 54 and follow along. As we're going through the webinar here, if you have questions, we will get those answered at the tail end of the webinar. Feel free to type those questions in the GoToWebinar box there on the right-hand side of your screen, and hope to get those questions answered at the tail end of the meeting today. With that, let me hand things over. I do want to introduce our panelists here. I am joined by the president and CEO of Mescope, my dad, Mark Richardson Sr. In addition, we have a director of engineering for Vibrant, Brian Schwartz, who's also joining us, and the two of them will be going through a lot of the presentation. With that, let me hand things over.
Okay,
Brian,
thanks, Mark.
Who's starting?
Brian has been with Vibrant. I am not the president of Mescope, I'm the president of Vibrant.
Did I say Mescope?
Many people, and especially when we go to trade shows, they come up and they say, oh, I know all about Mescope, but I've never heard of Vibrant. I didn't realize what your company was. But anyway, Mescope, and the VES stands for Visual Engineering Series. So we've had that for this, we're going into our 32nd year in business. This is the only product that we sell and support, the Mescope software for experimental modal analysis and ODS. And in the last 3 years, we've been developing and promoting, and we've added video processing, post-processing. And it's very much a complement to using accelerometers or lasers or any other type of measurement device. And even more so, we've been focused on using your cell phone as an acquisition device for especially extracting the vibration from operating machinery in a plant. Anyway, we're going to talk about something different here today. And so let me scroll down, and I'm going to do most of the talking, but Brian Schwartz has been with Vibrant for many years and has a strong background in FEA as well as experimental modal analysis. So we'll cover this subject today, and Mark, I don't recall whether you mentioned that we're going to do another webinar probably right after IMAC when we get back home here. And of course, we're spread around. Brian Schwartz is in Texas. I'm in Southern California, and Mark is in Denver. So anyway, we're using the power of the internet to do this presentation today. What is impact testing? Here's just 4 bullet items that kind of refresh most of you if you're familiar with impact testing. The reason we impact the structure is that impacting applies a broadband force signal. By broadband, we mean many frequencies from DC up to typically a kilohertz, couple kilohertz, depending on the size of the hammer and the size of the test article. I've even tested vehicles from the space shuttle program, bridges, and then tiny items also. So impact testing is very versatile. It was developed back in the 70s, both at Hewlett-Packard, where I used to work, and also at the University of Cincinnati. A professor there named Dave Brown was one of the pioneers in the use of an impact hammer. So it's very handy for testing a lot of things. And even with an operating machine, it's called bump testing. You can apply an impact signal to an operating machine and extract resonant information from it. We're going to simulate an impact test here today, and what we're calling rapid impact testing, you'll see in a few minutes, is quite different than the traditional way of doing things. All you need to do an impact test is a data acquisition system that simultaneously acquires. Now, when we say simultaneously acquire the force and the response, we mean that we create digital signals from the analog signals. So the sensors, the load cell and the accelerometer, create a voltage that is processed in a acquisition system, multi-channel. Typically it's called multi-channel, or an analyzer. Up here in the title we got FFT, or 2-channel analyzer. That typically is an acquisition system that can do this next line here, the frequency response function calculation, or an FRF. Very common measurement type that's made when we impact a structure. Here's a definition of an FRF. It's the digital frequency transform, the DFT. Again, these are commonly used terms, but we use them a lot at Vibrant, just so that we're all on the same page. There's a lot of terminology. Some people would just say, well, that's the FFT. The FFT is an algorithm that creates, you can see down here in the picture, it takes the digitized time waveforms, which we call TWFs, does a Fourier transform on them, and creates digital versions of the spectrum of the signals. So here we call that a digital frequency transform, or spectrum. You can interchange those words also. So we get both a DFT of the accelerometer response and a DFT of the force. Both of those are simultaneously measured. And so we need 2 channels that simultaneously sample and filter and condition the signals, amplify them, whatever goes on in the acquisition equipment to provide to TWFs, which then are converted into FRFs. Then we go through a process of curve fitting, and we'll do some of that later in the webinar. And we extract 3 fundamental properties of every structure that vibrates, which is virtually everything. If there's mass and elasticity in the structure, it will vibrate if you apply a force to it. Even the earth, I've experienced it out here in California. Earthquakes cause the surface of the earth to resonate, only for a short period of time, but I've actually witnessed it during earthquakes. Okay, so let's move on. Now, here's a key issue here. Resonance peaks occur in an FRF. So that's why we make that type of a measurement. Now, a couple of weeks ago, we had a webinar, some of you might have been in attendance, where we asked the question, do these 2 type of impact tests yield the same information? And this was part of another app note, and we have over 50 of them on our website. So if you have a license to Mescope, you can go out and use these app notes for self-training, or even use them among yourselves as engineers to get familiar with this type of testing. Anyway, a roving impact test is the one on the left. That's where the accelerometer that's measuring the response remains fixed to the structure, and the impact hammer roves from one point to the next, and it can even be in a different direction, and that would be a unique measurement also. And then the test on the right is a roving response test, where the impactor is applied at the same point, same direction throughout the test, and the accelerometer, in this case a triaxial accelerometer, is moved from one point to the next. So these are the 2 simplest ways of doing a impact test. And of course the question was, do they give the same modal information? Now, up here in this previous slide, the modal information that the question was asking about are the frequencies of the resonances, the damping of each resonance, and the mode shape, which is the spatial deformation of the structure at the resonant frequency. So those are the fundamental properties of resonant vibration. And as I said, most structures that we experience here on Earth especially have all 3 properties. They have frequency, a resonance has frequency, it has damping associated with it, and it has a characteristic deformation, spatial deformation over the span of the structure, which we call the mode shape. So let's move on. Okay, we're gonna simulate a roving impact test, or in this case, we're going to do a rapid impact test, and we'll see the difference. But here's a traditional roving impact test, a picture of how you would do it. The accelerometer remains fixed, and the structure is impacted at different DOFs. A DOF is a point and a direction. So at any single point on a structure, I can have 3 DOFs. I can have, and again, we're talking about translation. We're talking about just motion in a direction. Actually, I can have an infinite number of DOFs because I can just keep changing the direction of motion. So on any real structure, there's an infinite number of DOFs at each point. But typically, we break things down to X, Y, and Z, or horizontal, vertical, and transverse, horizontal. You can see the little XYZ axis down here. That's typically how and that will capture the 3D motion of any point if we have a sensor that can sense that. But in an impact test here, the roving impact, the accelerometer, the DOF of that reference sensor is not part of the test, really. It can be anywhere. Well, it is a part of the test. We want to pick what we call a sensitive point where the structure is vibrating. If we put it on what we call a node point of a mode shape, that's where the structure is not moving at all at that frequency. So we want to pick active points or sensitive points for a fixed reference in a roving impact test. And then here it's depicting 4 impacts at points 1 through 4. The other thing to notice here is that the FRFs are labeled with a particular type of a label where the roving point number is followed by a colon, and then the reference DOF, in this case just a point because everything's just in the vertical, is part of the definition of that FRF. So what it's saying is that every FRF is the dynamics between an input point and a response point in this case, or an input DOF and a response DOF. Okay, so here's another key issue. I've already addressed this, and that is that each FRF is identified by the hammer DOF and the accelerometer DOF. In this case, the DOF is just a point number and no direction associated because everything's in the vertical. Only the roving impact DOFs define the ODS or mode shape DOFs. So again, if we're going to define the spatial deformation of the structure, an ODS and a mode shape, we won't get into the difference between those two. Let me just suffice it to say that all ODS data is what we acquire experimentally, and every ODS is a summation of contributions due to mode shapes. That's all I want to say about that. We can come back to that if you have any questions, but let's move on and look at some live data off of this aluminum plate, this flat plate. So this is some real data that was taken off of a plate where we impacted it with a roving impact test. And so in Mescope, the properties of each FRF are listed in what we call the impounds or measurement numbers spreadsheet on the right side. So when you open up a window in Mescope with some data in it, either time and or frequency, in this case, they're FRFs, which are functions of frequency. So you can see the frequency axis down here on the bottom. And then this is just log magnitude. So the log magnitudes and the units are G's per pound. So what is that? Well, the units are the units of the accelerometer response divided by the units of the force input. So if I want to get scale data, and I'm going to go on and use it for other reasons, and we'll get into that in a minute also, then I want to scale my sensors when I'm acquiring the data so that the digital data that I end up with from the acquisition front end are in engineering units, pounds of force, G's of accelerometer response. Okay, the other thing in this impound spreadsheet are the DOFs of the FRFs. So you can see that in a roving impact test, the DOF in front of the colon changes between measurement 1, 2, 3, 4, and the DOF behind the colon is the reference. In this case, it was 1Z. So 1Z could be anything. It could be like it shows up here. It could be 31Z. Doesn't matter, because the mode shapes that we get from the data are going to be defined by the roving DOF. Okay, so let's get into curve fitting now. This is where things become a little mysterious for those who haven't had experience using a software package like Mescope. The key step in doing broadband testing, either with a shaker or an impact hammer like we're talking about here today, is that we excite many resonances simultaneously with the force. And then we have to go into these FRFs that have peaks in them and do what we call curve fitting. Now, curve fitting is a process of matching an analytical or a mathematical model to the FRF data. And in the process, we identify the unknown modal properties: frequency, damping, mode shape. So what do we get out of it? Well, we get the peak, the strength, or each peak we get frequency, which is the location of the peak along the frequency axis, damping, which is the width of the peak. We won't go into that in details today, but the higher the damping of a mode, the wider its resonance peak in an FRF. And then what we call the strength of the peak is also called a residue. And that's a mathematical term that comes from calculus. Some of you mathematicians may be familiar with it. It comes from integrating around a resonance, which is also a singularity. And the remainder, what's left over after we do that contour integration, is called the residue. So just like the common use of the term, something I throw away in a trash can or something that goes down the sewer pipe is residue. And that's what it means. However, the higher the peak, the greater the strength, and the residue number, the magnitude of the residue is greater. So you can see down here in this is called a shape table. This is how we store the data, modal data, once we go through this curve fitting process. And you can see each shape here has a magnitude and a phase, or a real and imaginary, same thing, again, mathematically. Most engineers like the idea of magnitude and phase better. So you can see these phases are kind of random. The magnitudes are, again, the strength of each resonance in each measurement. So the residues from a single reference set of FRFs, which we would result from a single reference modal test, contain the mode shape of the resonance. And the DOFs here, you can see the measurement type. This is called a resonance or residue mode shape. So RES, SHP, residue mode shape, because we got them from curve fitting. You can see the units, they're a little different than the units of the FRF. They got seconds in the denominator along with the pounds of force. And then, but the DOFs are the same as the DOFs of the FRFs. So now we're going to get into the whole issue of testing and the practical problem of testing a large structure. So here we have a kind of a small structure. It looks like a little beam, but just imagine that to be a bridge or a large space structure, launch vehicle, whatever. I've had experience over the years of testing bridges and space shuttle launch vehicles, very large. The impactor, of course, is larger, and the accelerometer can be larger, but typically there you use an accelerometer that will sense lower frequencies. So as you go up in size of any mechanical system, structure, machine, you want to make sure you capture the lower frequencies. Okay, so here's a picture that shows an impact hammer with a load cell that's going to measure the force. The accelerometer is going to measure response. And this is a roving impact test where I can locate the analyzer close to the accelerometer with a short wire. So we're assuming that this is a more traditional way to do it. Now we're getting into the use of wireless sensors and video to do this type of testing also. But more traditionally, if you're going to go out and test a structure, a car body or something, and you want to, or a frame, and you want to get do a roving impact test, you're going to need a long wire to go from the load cell to the analyzer. So here is the difference. If the analyzer can be moved between acquisitions, and we have lots of portable analyzers now, battery powered, small analyzers. In fact, I'll mention right here that with our rapid impact testing software and a 2-channel analyzer, Modal Shop, which is one of the vendors in our business, offers a 2-channel analyzer for about $1,000. So if you own Mescope, we have a $1,100 option that will work as an acquisition front end. We'll look at that in a minute, to that 2-channel analyzer. And so for $2,100, you basically have a dynamic signal analyzer, 2-channel, for doing this type of thing. And again, the analyzer plugs into the USB port of a laptop, so you can just do a rapid impact test with very low cost equipment these days. Back when I started in this business at Hewlett Packard in the 70s, a 2-channel analyzer was $100,000 in that money. And now today it would be ridiculous, but the hardware costs have come way down. Okay, so if the analyzers move between acquisition, I can do it now with 2 short wires. However, I need processing, and Mescope has it. We'll look at that here as we go along for processing this data. So now I can, here's some more comments. Rapid DOF, okay, both the impact DOF and accelerometer DOF can be changed between acquisitions. However, we need to form a chain of acquisitions, and we'll see that in a minute. The chain of FRFs is calculated from the chain of time waveforms. So everything starts off by capturing the dynamics with time waveforms and then using FFT processing and other signal processing. But this is not a single reference impact test. So that's the point of a rapid impact. Okay, so this is getting into a little bit of mathematics. Hopefully it won't put you all to sleep, but it's showing the difference between, here on the left, a mode shape, and the mode shape's got 3 components, MSC 1, 2, and 3, and residues that I obtained by curve fitting some FRFs, and the residues would be between 0.1 and 2, 1 and 3, and 2 and 3. So these are rapid impact test residues. They don't have a roving impact in front of the colon or a roving DOF and then a fixed DOF following the colon. But this is how in Mescope we process that kind of data and come out with, well, this is just simply showing that these residues are the product of 2 mode shape components. That's the key in the mathematics that you need to understand. So modal residues are obtained by curve fitting the FRFs, but they don't form a mode shape. We can use the same curve fitting that we use for single reference curve fitting to extract the residues. And the whole idea behind rapid impact testing is this relationship between the residues and the mode shape components. There's a little more details over here. I'm going to go ahead because I want to get to the simulated rapid impact test. And this is the subject of App Note 54. So let's look at this. We're going to simulate a rapid impact test with this flat aluminum plate. You can see it's got 30 test points on it, and the first measurement we're going to call a driving point. Now if we look back here just quickly, you can see that if I have a driving point, then I can get started processing this data, because the driving point residue is the product of the same mode shape component times itself, or squared. So if I take the square root of that number, then I can get started with this post-processing. But here's the way the rapid impact test would go. Like the first time we hit at the driving point, and that's a hard measurement to make sometimes, but experimentally there are tricks we can use to where the accelerometer and the impact hammer, the DOF, is the same. Now we go over and we move the accelerometer to 0.2 and impact again, take another set of data. And then the third time we leave the accelerometer alone and move the impact. So now we're going to go to the steps of this application node, and I'm going to run Mescope and show you how all this is done. Now in Mescope we have something called scripting. Now those of you that own Mescope have probably never used it. It's a standard part of Mescope, and each script can have a hotkey associated with it. So these are just like commands. If I press a hotkey, it will execute a script, and it will cause Mescope to do a whole bunch of things automatically. Let me just show you one here. Okay, so the script is just a spreadsheet, and here's the target window command. So I can execute any command in any window in Mescope. I put in the name of the window, I put in the command, and then when I execute this script, it's going to execute each of these commands in this spreadsheet. And this one here happens to be fairly short. And it just rattles through each line of the spreadsheet and executes the Mescope commands. So that's what that's all about. Let me put this back down, and here's our test article. You can see our 30 points. And the first thing we're going to do is simulate some random impacts. So I'm going to build up a data block of data that has random impacts in it. So let me just go ahead and push that, and you'll see a bunch of stuff happen in Mescope. And then when it's finished, you can see over here, it's building up a data block full of time records. Bingo. So these are time waveforms. Okay, here's a little message of telling what happened. Again, this is part of scripting in Mescope. 30 time waveforms were created with 3 random impacts per waveform. Scroll through the impacts. So here they are here. If I scroll through these impacts, you can see that they're just 3 impacts in the time domain that have random magnitudes. So this would simulate, a real impact test where you can't control the level of the impact. You're just gonna hit the thing with a hammer, and you're doing the impacting, and these are all randomly stored here in a data block. And you can see there's 1, 2, 3 of them for each. So if I go over here in the spreadsheet, you can see the units are pounds. They're all labeled as an input. That'll be important here in a minute. They're time waveforms, and they have DOFs. So the DOFs, you can see the DOFs are a little strange. There's 1Z, 1Z, and then 3Z, 3Z, 5Z, 5Z. Well, those are the points where we're gonna actually apply the force to the plate. 0.1, 0.3, 0.5, 0.7, and so forth. So we're not even gonna ever hit this thing at 0.2. We're just gonna jump over to 0.3 with the hammer. Now, with the second measurement, we're going to move the accelerometer to 0.2 and make a measurement there. So that's what we showed in the, if I go back here just real quick, we can see here that the first impact's going to be a 0.1, the second impact's going to be a 0.1, but the accelerometer is going to move. Then we're going to move all the way to 0.3 with the third impact. So that's what's going on here in this simulated impact test. There's something else in here. You can see some square brackets with a number in them. That's what we call the measurement set. So when we do processing of our data in Mescope, this is all just record keeping. This is telling Mescope, okay, the first time I took data, it was measurement set 1, and then 2, and then 3, and then 4. And if I want to match up my hammer data with my response data, we use measurement sets in Mescope to do that. Okay, let's go back here and go to the step number 2. So here we are, we created the random impacts. Now we're going to create random impact pairs. So we're going to do this with something in Mescope called MIMO, multiple input, multiple output. And there's several commands in Mescope for doing this. And what we're going to use are these are called UMM mode shapes. Don't go into that right now, but when I scale the mode shapes properly, this is another difference between an ODS and a mode shape. ODS has certain engineering units based on, my accelerometer or however I took the data. With a video, the units are going to be in displacement. With an accelerometer, the units will be in acceleration. Mode shapes don't have any units, so I can scale them in different ways. And one of the ways that we scale mode shapes is what we call unit modal mass. I'm not going to go into the mathematics behind it, but Mescope has a way with experimental data of scaling my mode shapes. Now, an FEA program will solve for unit modal mass mode shapes. They will come out scaled that way, typically, from an FEA package. Okay, so we're going to go in and use these UMM mode shapes, which are scaled, and what it means is they have engineering units associated with them, whereas a mode shape in general has no units. You can scale it any way you like. We're going to go into MIMO with these, what we call a modal model, these unit modal mass mode shapes, synthesize FRFs, feed in the time waveforms, again, the random impacts, 3 of them, go through all this processing, and out come the response of the accelerometers. So let's go back and do that. Mescope can simulate all of this. I'm going to push the rapid impact pairs, and now it's going to do all this processing using MIMO commands. Again, it's executing another script that is connected to the rapid test pairs. And you can see what's coming out here. On the right are the accelerometer response. And now it's doing some more processing because it's putting the impacts together with the responses. And again, this is where it used the measurement set numbers to match things up. So it's saying we got 30 sets, so same amount of data that you would typically take if you were doing a roving impact or a roving accelerometer test. But over here, let's just look at what we got now. The red ones are the forces, and the blue ones are the accelerometer responses. These are all time waveforms. The forces are inputs, the responses are outputs, and you can see that this is how the data is labeled for each of the measurement sets. So measurement set 1, number 2, number 3, number 4. So let's go on and acquire. Now this is where we're going to take this data, and so if you did nothing more than take a 2-channel analyzer and acquire this type of data, import it into Mescope, you could do the next step, which is process this data, and with what we call an acquisition window in Mescope, and you'll see it has graphics that goes with it. We can actually put a little hammer on the 3D model, so you have to have a 3D model at this point if you're going to process your data. And if you own Mescope, we have a whole model store with lots of models for machines and car bodies and all kinds of things. But I'm going to let it go here. You can see that it's actually showing you graphically how it's processing this data. Now it's going to say, do you want to continue the acquisition? And in the interest of time, we're just going to go ahead and do, I'm going to say no. So now you're going to go through and you can see that the acquisition has processed all the data. I've got 30 FRFs. These are the rapid impact FRFs and their associated coherence. And it says scroll through the FRFs. So here they are. Again, this is typical data that you would get from in any modal test. And the coherence is the red, the FRF is the magnitude is the blue line, and there's phase in here also, but this is just showing the magnitudes and the coherence. You can see at low frequencies it drops off quite a bit, but that's okay. We're really only interested in the data around each of the resonance peaks. Over here you can see the units, G's per pound, and again the blue are the FRFs and the red are the coherence. Let's go ahead and do the next step, and that is the curve fitting of the FRFs. Now we're going to use single reference curve fitting here. Okay, the script is processing this data, isolating the FRFs, and bingo, it's already done, and it says the curve fitting is complete. Rapid test residues are saved in a shape table on the right. So over here on the right, here's our curve fitting results. You can see these rapid test residues, RPT, rapid test residue, magnitude and phase. The label shows the curve fitting method that we use to get the results. And you can see these residues have units of the FRFs. Same units, and we've got 30 of them in here because we had 30 FRFs. So, and then over here is the curve fitting. Now there's a red curve fitting function laid over the FRFs. Now again, even though we had signal processing, we had 3 impacts, we did some signal processing to create the FRFs. This is almost ideal data. I mean, this is like it came out of a textbook, but it's a real simulation of the real thing. And then down here is what we call the, well, it's a mode indicator. So it's a sharp peak showing where the curve fitting found each of the resonance peaks and did a curve fitting. And then over here is the modal parameters and some curve fitting results here. All right, we're going to move on residues to unit modal management. So we're going to convert these residues because they're rapid impact test residues. So again, this is something unique to Mescope. Rapid impact test residues are displayed on the left, and they're converted to unit modal mass mode shapes. Again, this is something going on in Mescope to convert, and you can see they're in inches per pound second. They're scaled. These are unit modal mass. And then over here are the residue mode shapes, which are different magnitude values for sure, but the frequency and damping are roughly the same because we got the results from curve fitting. Step 6, we're going to get close to the end here. Rapid test mode shape on the left, the original EMA mode shape with maximum MAC on the right. So here we're comparing in a comparison animation, we're comparing the results of the simulated rapid test on the left with the results that we started with on the right, the UMM mode shapes to simulate using the MIMO calculation. We fed input into the model and we got the accelerometer response. So this is what's called a sweep animation through the 2 data block or 2 shape tables. You can see up above here are the rapid test mode shapes. Each of them has frequency damping. Now this says frequency or time. I can have ODS data that is time-based. We call it a time-based ODS. That's what we typically get from a video. But mode shapes are typically frequency. they always have a natural frequency associated with them. You can see the damping is a little different here, but basically we got the same results back. Up here are two numerical measurements that we use in Mescope of a comparison of two shapes. So MAC is an acronym for Modal Assurance Criterion. That's a very common way to compare two mode shapes. When the MAC value is 1, that means the two mode shapes are essentially the same shape. Now, SDI is something that's unique to Mescope. That stands for Shape Difference Indicator, and that compares the shapes numerically. Do they have exactly the same numerical values? Now, if I look at the shape table here for mode shape 1, as you can say, this is 31.68 down here. It's a little different. It's 30.39. So they're not identical component for component, but when this says the SDI value is 1, that means that they are very close, comparing all the numerical values of one shape to another. And as we scroll through the different mode shapes, you can see that both these measures, and essentially what that's saying is we did a round trip here with this simulation. We started out with some mode shapes and we ended up with exactly the same mode shapes. Let's go back here. I'm going to click on the first one. Okay, I think they're all 1s, which is pretty amazing. That's very good. Now, if I had FEA mode shapes and experimental mode shapes, let's say residue mode shapes, the MAC values could be 1, but the SDI would be quite different because the mode shapes are scaled differently. Anyway, that's pretty much it. Let me go back and let's just make sure we've covered everything. Step 2 was the random impact pairs. This is the ACK window where we went through very quickly all the acquisitions. We could go back and look at that if there's any questions about how we did that. Here's the curve fitting step where we curve fitted the FRFs, and the fit function is in red laying over the FRFs. They were colored blue up here. So, and then down here, the comparison between the residue DOFs that we got from curve fitting, the rapid impact residue values versus, now that's not a mode shape over here. These are just numbers that have different DOFs. The DOFs are associated with the rapid impact testing. Over here, the mode shapes are for each of the points, the 30 points and the Z direction on this structure. And then we did a comparison and we saw that sure enough, the round trip, we got back the exact same values. So Mark, that pretty much wraps it up for me. Brian, do you have any other comments?
No.
Do we have any questions?
We got a couple questions. If you do have a question, go ahead and type that in the box right now, and we'll go ahead and get that answered. We got a few minutes left here. Alvaro says, hi Mark, could you explain shortly how is calculated the modal mass and modal stiffness, for example, at the second mode or any mode? How the modal mass or modal stiffness is calculated?
There's a lot of mathematics behind that. I think we explain that in one of our app notes. I'm not sure which one, but modal mass and modal stiffness are mathematical terms that involve in an FEA pre and post multiplying a mass matrix and a stiffness matrix by mode shapes, and that gives us modal mass and stiffness. Now, we're not doing any of that with experimental data. We're just doing what we showed here in the simulated rapid impact tests, However, since all the data has been properly scaled, and that's important that I scale my force data with pounds of force and my accelerometer data with G's of acceleration, then in Mescope, we can rescale that data as if we actually had the mass and stiffness matrix for the experimental test article, which we don't have. We don't have a mass or stiffness matrix, but we can still scale the data as if we had that mass and stiffness. And then, of course, scaling it to unit modal mass is simply saying, again, the mode shapes don't have any units, engineering units associated with them, but if we want to preserve the mass and stiffness of the structure that we actually tested, we do that first by scaling the force and accelerometer signals, and then scaling the mode shapes to what we call unit modal mass. And that's just a way of preserving the dynamics as if we had the mass and stiffness matrix, but of course we don't have it. There's plenty of mathematics in our tech papers and in some of our app notes that will go into the details if you want to kind of go through it all for yourself. But that's a good question, because that's
application note 28 is probably the first place. It goes through all the mathematics with a single degree of freedom system.
Yeah, well, again, you know, Vibrant, our logo is a mass on a spring with a damper. If you understand all the dynamics behind that, you'll understand the dynamics of a space shuttle, a car body, whatever you're testing, because it's all the same. Mechanical systems and elastic structures, any structure with mass and elasticity in the material properties is going to have the same mathematics as the mass on a spring with a damper. That's how we analyze the data. Now that's all linear, and we won't get into all those details, but it works surprisingly well in the real world. And so that's why we can do modal testing.
Pat McCarg typed in, he just wanted to remind us that the biggest benefit of rapid test is that you do not have tons of wires to route, just the lines for the reference and response. Just a reminder. Yeah, it's good.
And Pat is one of the engineers at Vibrant, and he and I have tested several bridges back in the early days of Vibrant, and we would spend at least an hour every morning before we took any data just running wires. And you know, we were doing a roving response test where we moved the accelerometer over the bridge truss in both cases. We actually had a grad student who we left up on the bridge who mass loaded the bridge, but we didn't care. And he was willing to stay up there on the bridge truss and move the accelerometer along. And then we impacted the bridge at the same point, same direction, with multiple impacts, and took data that way. But we had to run wires all over the place. And so, yeah, Pat has suffered through that in his career, and any of us. So that this is where rapid impact came from. And in fact, what motivated us to put the post-processing of the data into Mescope was some students we had in class from an oil refinery, and they said, you know, we do impact testing on pipe systems all the time, but we have to run a wire. You know, if we're doing a roving impact, we've got to run the wire, a long wire from one end of the pipe to the other. Can't you guys come up with a better way to do impact testing? So that's where it came from, testing pipes in refineries.
Okay, just got a question in here from Chris. If I'm testing a small structure where the wire length is small, is there a benefit to this process over a traditional testing?
Probably not. Probably not if you don't have to deal with long wires and larger structures. then you can do a traditional roving impact or a roving response, either one, depending on which one's the easiest. We haven't done it yet with Mescope, but other companies have done it, and that would be interesting to do on a small structure using a cell phone to measure the response and then impacting it with a hammer. So that would be a unique thing to do. But if the accelerometers are very small and cheap now, so they won't mass load even if you rove the accelerometer around on the structure and impact it at a single point. So yeah, I mean, I wouldn't bother doing this unless you got something larger. Good question.
That's it for the questions right now.
Well, we burned our hour.
Yep, I think we'll look at doing our next modal webinar the week of February 20th, which will be the week after IMAC. So stay tuned to your emails. We'll get an invitation out to you. And what are we gonna do in the next one?
We're going to do the same thing. So come back for a review, but we're going to use the triaxial accelerometer instead of a uniaxial. So for that, you would need a 4-channel analyzer, and there are very many, there's lots of them, and Mescope will work as well with a 4-channel as it does with a 2-channel. And so we'll go through this whole thing again, and that's a different app note out in the cloud from the Vibrant website that goes through a simulated test just like this one here.
Excellent. All right, well, why don't we wrap it up there? Again, if you want to go back and review this webinar, we'll get this posted out to our YouTube channel here, and it's just a couple days. It usually takes by the time it gets processed and so forth. So perhaps by Monday, we'll have that uploaded to the YouTube site. We did get one question here from Ed. Did you say something about using a camera and a hammer?
Yeah, I just said that.
You did.
We haven't tried that yet, but Mescope has the ability to process camera data now and get responses. And we've done some comparison of accelerometers and the video, and they can match up very well within, let's say, good engineering practice, where you can get two. I think one of the videos is on our website where we do a quick comparison of the accelerometer response and the camera response.
Yeah, comparison, right.
Comparison, and you can get two decimals of accuracy, which, in practice, engineering practice, is plenty good. So we've done some of that, and we are convinced that a video properly scaled can get accurate response data.
Great.
Anyway, a good question, and that would be something to try. You could go to IMAC and present your results there. That would definitely be a good technical paper with some good results to show. We're going to show a bunch of video results at IMAC, but they're mainly from what we call operational mode shapes, extracting mode shapes from, and ODS data from video data taken on an operating machine. Now, again, 3D, an accelerometer can measure 3D motion at each point, so sometimes that's very helpful. Different resonances can have dominant motion in one direction, and then the next resonance is dominating in a different direction. With something simple like a flat plate here that we're looking at, not so much the case. But as you go up in frequency to higher and higher natural frequencies, you'll see more 3D motion in the mode shapes typically. So a video camera, your cell phone is only going to get 2D motion in the frame of the video itself, in the plane of that you're using. Now you could, in Mescope, you could put data together from several different points of view. And if you're using impact testing, then, you know, you'd have to have some way to extract the data from the impact test properly without synchronizing. Now, more expensive systems and competitors are, you know, selling $250,000 systems that will synchronize 2 or more cameras. With a cell phone, you can simply take data from different positions. So again, we haven't tried that, but in principle, it should work.
Excellent. Let's go ahead and wrap it up there. Again, take a look at the YouTube site. We got lots of great videos out there. I know there was a question about aliasing. We got a video on our on the YouTube website about aliasing. And so you can get some more of that information, as well as what we just talked about, a comparison of videos and accelerometer. There's another video about that as well. We did a webinar earlier this year. So if you got any questions, always reach out to us, sales@vibetech.com. And with that, I will say see you later. We'll see you at my IMAC.
All right.
All righty. Have a good day, everybody.